Okay, thank you for the introduction. Today, the topic I'm going to cover is called mean-field game. I still remember my first project on mean-field game is collaborate with my PhD advisor, Professor Lai, with Professor Osher, and Professor Lai graduates from UCLA, obviously, and also with Professor Wuchen Li, who was a postdoc here. And the work today is joined with my postdoc mentors at Duke, and two of them also graduate from UCLA. So I feel very happy and grateful to have the chance to present it here. So the topic is called learning and inference in mean-field games. So to begin with, let me say a few words about what is a mean-field game. So the thing is, we want to consider a system with a continuum number of players. Basically, there are infinitely many players in the game, and all of the players, they are indistinguishable in the sense that they have the same objective, and every individual does not change. The change of each individual's strategy will not change the population density. But in the game, they are not cooperating with each other. In the game, every individual is looking for some best response, looking for some optimal control to minimize its own cost. And the thing is, their cost actually depends on the population distribution. At the same time, if each individual is making some decision, then their aggregation behavior will reformulate the population distribution. So there is some interdependence between the population and the individual level. And mean-field game, the goal of mean-field game is to find the Nash equilibrium, which is the place where the individual agrees with the population, or you can understand it as the fixed point of this back and forth process. So there are typically two formulations of mean-field game people usually work with. One is the PDE formulation, which is the coupled system of a HJB equation and Fokker-Planck equation. The HJB equation comes from the optimal control, and the Fokker-Planck equation comes from the aggregation behavior. The difficulty here is these two equations, they are coupled through this interaction cost and terminal cost and this driven term. And another formulation that is more favorable in machine learning community is this variational formulation, and sometimes it is also called mean-field control. The idea is if your interaction terminal cost, they derive from some potential, then you can reformulate this coupled PDE system as an optimization problem, which after some change of variable has a linear constraint and some convex objective. So you have many algorithms to deal with it. Traditionally, mean-field game is very favorable in economics because it's natural to use mean-field game to study a system with many players. Before mean-field game, in classical game theory, when you need to consider the interaction between individuals, you need to consider both the state distribution and the control of each player. But when you have many players, this becomes inaccessible. So the good thing of mean-field game is when you have a continuum number of players, you don't have to care about the control of each player. You only need to look at the distribution of the population. And another thing that, so recently, because mean-field game finds connection with many machine learning models and applications, it's more and more popular. For example, it's naturally used to study multi-agent reinforcement learning, where you have many agents. They not only interact with the environment, but also interact with each other, and they are not cooperating in this control problem. And for this variational formulation, it also finds natural connection to optimal transport and some generative models. So for example, if you take a special interaction, if you take the interaction cost to be 0 and the terminal cost to be some indicator function of the desired density, then the problem becomes exactly the Benamou-Grenier formulation of optimal transport. And also in flow-based generative models, people care about how to move from a simple distribution, say Gaussian distribution, to the data distribution. So they actually want to find the path on the probability space. Optimal transport typically find the shortest path, and with mean field game, we have more possibilities. We can consider some interactions that may give us some faster paths, because shortest may not be the fastest. So in short, there is a high demand on solving mean field game, for example, in high dimension or even in non-Euclidean space. But the thing is, this mean field game system appears only in the recent 20 years, and people's understanding of it is not as good as other equations such as HJB equation and Landau equation, that type of thing. So what we want to do is we want to, there are some PDE analysts and the probabilities to study of mean field, the existence and the uniqueness, that type of thing of mean field games, but we feel there are still some missing parts. We still don't find the key to understand this system. So the work I'm going to present today wants to give some insight on this. The first thing we do is we will give a convergence analysis of a forward solver, which is called fictitious play. This fictitious play is already exists in classical game theory and adapted to mean field game recently, but the convergence analysis is still not clear before our work. And this, the study of this project looks like a puzzle. At the beginning, it looks like you don't know where to start. But once you find the key, which is the best response, later you will see everything becomes clear. Everything is centered on this concept of the best response. And then I will show a numerical algorithm to solve a class of the inverse mean field game. And while we don't have the convergence analysis yet, but I think there are some insight information that's worth to share. So I want to note first that this talk doesn't contain any usage of deep learning method or analysis of deep learning, but I hope at the end you think there is some insight that can help you. Okay. So let's start from mean field game and fictitious play. What is mean field game? Let's recall it's a coupled system of the HJB equation and Fokker-Planck equation. For simplicity, I will assume the terminal cost is fixed and doesn't depend on the density for the rest of the talk. But as long as you have the interaction cost, the problem is not oversimplified. So the difficulty of solving this system is not only because they are coupled, but also if you look at the HJB equation, it's moving backward in time, and the Fokker-Planck equation is moving forward in time. So if you want to solve the system, you need to couple the time and the space domain. And there are some nonlinearities, so directly solving it is not an easy task. And fictitious play has a very simple idea. Is say, how about I decouple the system? I first solve the HJB for a given density probability distribution rho. Then I use this phi k hat to move my density rho with the Fokker-Planck equation. And at the end, I do some average on the density. So when I first saw this algorithm, the first question come to my mind is, why not use fixed point iteration? Why do you have this average step? Because you see, mean field game is actually looking for the fixed point of this process. And shortly, you will see fixed point iteration may not converge, and it may oscillate between two states. And I will show a hand-wavy result on why this will occur. And the next question is whether this algorithm converge, and what is the convergence rate if it converges. So all the existing works on the analysis of fictitious play assume there is a potential, so they can use the objective as a natural indicator or natural metric for the convergence. But for general non-potential game, there is no such thing. And our goal is we want to develop the convergence analysis for general mean field game without assuming the existence of the potential. Okay. So as I promised, I show you fixed point iteration that actually may not work. The idea of fixed point iteration is, say, every time all the players, I just naively take the best response and to the latest population density, and for all the history information, they didn't use it. And numerically, we can show even for the simplest setting of mean field game, even you start from the Nash equilibrium, if you keep running fixed point iteration, it will lead to a divergence sequence numerically, and eventually it will oscillate between two states. Why this will happen? So first I will bring some concept to give you a heuristic idea of why this may happen. First is some definition of the monotonicity. This is we say F is monotone if this inner product is always greater than or equal to 0. If F derived from a potential, this actually corresponding to the potential being convex. This is a common assumption in mean field game to ensure the uniqueness of the solution. And we can actually prove that if I give you two rho 0 and rho 1, I first solve the HJB equation, got the phi hat. Then I solve the Fokker-Planck equation and get the rho hat. Then the inner product between difference of rho hat and difference between F is actually smaller than or equal to 0. So if you have a monotone potential, then you will have some figure looks like this. So these two vector, well, forgive me about the, I should not use vector, but this is an abstract idea. These two things actually lies on the different sides of this hyperplane. So then if I take rho 1 to be the Nash equilibrium, which is the fixed point, then rho 1 hat is actually just rho hat. Rho 1 hat and rho 1 will be the same, which is rho star. So you have this figure, which means the density and its best response always belongs to the two sides. So it is possible that when you run the fixed point iteration, you will oscillate between two states. Okay, this is just a quantitative property, and to give a more rigorous, to give a deeper understanding, we need to do some more careful quantitative analysis. And as I mentioned before, the first thing we need to answer is how do you find a good indicator, how do you find a good metric to study, to quantify whether your algorithm converges. So let's go back and think about where does the HJB equation, Fokker-Planck equation comes from. The idea is that it actually comes from this best response process. And instead of write it as a PDE formulation, we can actually write it as an optimal control problem, where the idea is I fix this rho and I look for the best strategy V tilde and the corresponding density distribution rho tilde that minimize this cost. Here is the dynamic cost. This is the interaction cost with the population, and this is the terminal cost. The constraint is just the Fokker-Planck equation. Okay. So you can easily derive that the PDE, this decoupled PDE, is just solving this optimal control problem. And for some nice property, in order for the constraint to be linear, later we will use a change of variable, use M instead of rho and V. So now we can use that optimal variation formulation of the optimal control problem to write everything, to write the Nash equilibrium. So the Nash equilibrium is just, I want to find the rho star that whose minimizer is still itself. And then what is fictitious play? Fictitious play is just I fix one density distribution, I solve for the optimal one for the best response, then I take the average. And here, for the rest of this part, I will use the blue color to indicate the population and the red color to indicate the individual. Sometimes the variable might have the same value, but their physical interpretation will be different, and use this color code will help us understand. So with this, we can define the gain of the best response. for a given rho and m, for a given population distribution, I can evaluate my cost with the current strategy. And I can also evaluate my cost with the best strategy. There is a gap between these two costs. By definition, this gain of the best response is always non-negative, and it vanishes only at the Nash equilibrium. So if we can show that this thing goes to 0, then we may be able to show that fictitious play converges. Okay. So then here is the outline of our proof. Basically, fictitious play, the key idea of fictitious play and the key reason that fictitious play success is it used the history, and which is the learning in the title. So the main analysis we did is actually two parts. One part is that we show there is some connection between the gain of the best response and the distance between rho and the Nash equilibrium, also the distance between rho and its best response. Another thing we show is that along the fictitious play, this gain of the best response actually shrink if you choose delta k wisely. So we can show that under certain conditions and with proper choices of delta k, our gain of the best response converges to the 0 exponentially fast, and our rho k converges to the Nash equilibrium. Okay. So trust me, the proof techniques are not difficult at all. If you give the statement to any math students with basic chain, they can actually prove it. But it may not be easy to notice this. So the first thing that plays an important role in this constant C is the strong convexity. Why do we have this? Why do we need this? If you look at this optimal control problem, your variable is this rho tilde. Your objective, the last two terms, they are linear in tilde, which is very simple. So the only thing that will change, that will affect the stability of this minimizer is the convexity of this term, which we call it R, is the dynamic cost. So, but unfortunately, R is not strongly convex uniformly in the constraint set. So we define this directional strongly convexity. The idea is just I take two pairs of rho and m, and I connect them. Then I can define this single value function. If this y is strongly convex in this connection, in this line, then I say R is directional strongly convex. And the nice thing is, if your dynamic cost is uniformly strongly convex in V, then as long as you don't pick the same pairs, you will have this strong convexity. And with this strong convexity, we can first show that if my f rho 0 and f rho 1, they are close enough to each other, then their corresponding best response will also be close to each other, affected by the convexity between rho hat these two best response. Then one step further, if we put some assumptions on this interaction cost f, then we can show if rho 0 and rho 1, they are close to each other, then their best response is also close to each other. And as a corollary, we take special rho and we take one of the rho to be the Nash equilibrium. We can show this inequality, and eventually we show if rho is close to the Nash equilibrium, then it is close to its best response. Okay. Another property that we need to get the convergence of rho is this strong monotonicity. So you can imagine in convex analysis, if you only assume convexity, then you may not get the convergence of the variable. You may only get the convergence of the objective value. So to get the convergence of this rho to the Nash equilibrium, we will need to have some assumption, a stronger assumption on this interaction cost, which is strong monotonicity. So with this, we can show if rho is close to its best response, intuitively that means it is close to be a fixed point. And mathematically, it is also close to the Nash equilibrium. So we develop a equivalence between these two metrics, the distance between rho and its best response and the distance between rho and the Nash equilibrium. And next step, we need to connect the gain of the best response with the previous two metric. And we can show that if the best response is small, then rho is close to its best response. The proof idea is also very simple, and the key to get this result is the constraint being linear. So my friend in optimization told me if you have a linear constraint, it's almost like no constraint. If we have no constraint and we look at this gain of the best response, we expand this first term at the best response, then the first order term will vanish because the optimality, and the only thing that is left is the second order term, and that is affected by this convexity term. So overall, we have shown that these two metrics, they are equivalent, and the gain of the best response is a good thing to indicate the convergence. And the next thing is, do we have the decay of the gain of the best response along the iterations? So here there are some simple algebra. As long as we have the convexity of the Hamiltonian, we can use the convexity of the dynamic cost and the definition of the gain of the best response. Eventually, we will get three terms. The first term is desired because we know G is always non-negative, and this will give me a decay. The second term, if you still remember the qualitative property we present for the fixed point iteration being unstable, you will see this is something positive, and that's not what I want. Later, I need to control this. And the third term, because we assume the monotonicity of F, then this term will always be negative, non-positive, and will not give me any trouble. So I can get rid of it, and the only thing we need to do is to control this thing. And if you look at this, because we show that if rho and if the two inputs are close to each other, the best response is also close to each other. So eventually we will get rho k hat minus 1 and rho k hat. And by the definition, this is proportional to delta k squared and of this distance. So look at here, the good term is dominated by delta k, and the bad term is dominated by delta k squared. So overall, as long as I take smaller enough delta k, I will get some decay property. And something even better is this gap between rho k and its best response can be controlled by the gain of the best response. So it is possible for me to get some linear convergence or exponential decay if you like. Okay. And the good thing is this C doesn't depend on the mesh size. So numerically we can see that we will have the linear convergence, and the convergence behavior is very similar on different sides of the mesh. Okay. So with this analysis, there is something we can do to accelerate the algorithm. For all the existing works, they take delta k, naively take delta k to be 1 over k plus 1 or 2 over k plus 2. So if you see here, the improvement you get every step is proportional to delta k. So if you have run the algorithm for a long iteration and delta k becomes very large, the improvement you will get will become very small. And that leads to a slow convergence, people observe it, but they don't have the solution to it. With this analysis, we can show that when this C is available, we can actually take some constant step size, and that will give us the linear convergence. When it's not available, we can take something as they do, and another thing we can do better is we can choose the delta K dynamically. The idea is the only thing I need to do is I want this term to dominate the unlikely term. And I can adapt the idea of backtracking line search from optimization and choose this delta K. So numerically, we show that even with a non-quadratic Hamiltonian and with some very complicated interaction term, we can show that with the backtracking line search, we can accelerate our algorithm. But if you choose some constant delta K that is not very good, you will plateau at some point. And if you choose the diminishing step size, the convergence will slow down when K goes to infinity. Okay. Is there any question before I move to the next part? Okay. So the next part, we are interested in some inverse mean field games. The reason we want to study this is, in practice, sometimes you may not be able to know what is the cost, what is the interaction cost, or what is the running cost. But the thing you can observe is the Nash equilibrium. For example, in stock market, you don't know what makes people to make the decision, but you can see what's the output. And in reinforcement learning, usually it's model free. You don't know what is the actually cost, but what you can see is the reward. So this is something we want to study. And to make things concrete, we first look at a very, very special case of the inverse mean field game. We want to ask, if I have some ambient potential Q, this thing doesn't depend on the density, doesn't depend on the T, it only depends on the state. If I have some cost that looks like this, and all the other things I already know it, whether I can infer this Q from the measurement phi at time 0, which is the value function at time 0. So if you look at this problem, you may ask whether this problem worth study, right? Because this is too simple. You just move this F rho T to the left-hand side, then everything becomes trivial. But actually it is not, because the thing is you don't have the measurement of this partial T term. So, and also theoretically, there are some work that prove for a general class of the interaction cost and terminal cost, they can prove the unique identifiability of the cost. But all of the work actually require this ambient potential to be 0. And another work that deal with this, what they can do is assuming Q is a constant over space, and then they can recover it. But this is still too much of a constraint. Numerically, there are also some solvers. For example, this work adapts a forward solver to the inverse problem. And in the iteration, every time they need to solve an inverse linear parabolic equation, which can be time-consuming. And there are some other works, two from Professor Osher's group and one from me and Professor Lai and our collaborator. We also developed some optimization-based algorithm with the to solve this problem, but we use a different measure, which is the density and the velocity field. So through this work, we actually want to ask what is the most informative measurement, what is something you need to collect that can effectively help you to recover the ambient potential. So there are still many open questions, and we still don't have a good understanding of this simple inverse problem. So in this work, we don't have any theoretical analysis, but later you will see numerical works pretty well. The idea of this algorithm is pretty easy. The previous complaint is I don't have the measurement of this partial t phi. Then how about when I have an estimation q hat, I can solve it and get the rho hat and phi hat, which is the estimation. Then I update my estimation of the q with the phi hat from the estimation and with the rest of the thing from the measurement. And this C is some constant to deal with a shift in the ambient potential. It's available, it's computable. So if you insert the Hamilton-Jacobi equation to this partial t phi hat, you will see that this update is essentially take the difference between these two terms that is evaluated at the value function. So it seems like this term from the measurement is very crucial. And let's look at numerically what do we have. So this is a Duke Blue Devil logo. One of my collaborators likes it because he thinks it's very impressive. So the idea is we use this as the true Q, and we run the forward solvers, find the measurement. Then we compute this measurement-induced term. So you can see, although the scale of this thing is not right at all, but many of the fine details are preserved in this term. And we can actually show that our algorithm converges super fast to a relative error to the 10 to the negative 4 in about just 20 iterations. In just one iteration, we capture a large amount of the information, and in just 18 iterations, we converge to a desired accuracy. So that tells us this measurement-induced term, this measurement really retains a lot of useful information of the ambient potential. And another thing that we find very surprising is intuitively you may think if I have a large viscosity, then the information might be diffused and it might be very difficult for you to recover the information of the ambient potential. But numerically, you will see if you have a large viscosity, the convergence is super fast. It's much faster than you have a large terminal time or you have a small viscosity. And another thing we notice is if you have a non-monotone interaction, if you choose a small viscosity, then the algorithm doesn't converge. But if you choose a large viscosity, you actually can converge super fast with a very high accuracy. So our interpretation of this is that actually the ambient potential is not diffused even you have a large even you have a large viscosity, but the trajectory. If you have a large viscosity, the players will explore largely of the entire space, and you will get enough information to recover this ambient potential. So we also have some accelerations. The basic idea of best response iteration is, say, previously every time you need to solve the forward problem exactly, but this can be very expensive. So how about we use the idea of the best response? I just solved the HJB and Fokker-Planck one iteration, then I use that to update my estimation of the ambient potential. And it turns out it's very effective. This BRI is say every time I just run the best response for one iteration, and I can also run it for 5 iterations. It can reach the similar accuracy as the equilibrium correction iteration, and it needs less number of HJB and Fokker-Planck solvers. Another thing is another interesting observation is, how about we solve the inverse problem on a coarse grid first, and then iteratively refine the grid. And it turns out it has a very similar behavior as the multi-grid method for some low frequency ambient potential. If you directly run equilibrium correction on the fine grid, you will need much more iterations than recovering a high frequency ambient potential. But if you use the hierarchical equilibrium correction, this can greatly improve the efficiency of the algorithm. And the last thing I want to mention is we find that there is potential important connection between our inverse mean field game and the classical inverse linear parabolic equation. So if you, for HJB, you can take a Hopf-Kohl transformation to make it a heat equation. For the mean field game system, you can also take a Hopf-Kohl transformation and make it a system of the heat equation. So the thing is here, after the transformation, you have this measurement of U0, this move forward in time, then move backward in time, you have the W0. So naively, if there is no interaction, and if there is no interaction and the terminal cost is also independent of the density, then this is just the inverse linear parabolic equation. And there are many theoretical studies on this and many algorithms for this. And we also find that in 1991, Isakov proves the existence through an iteration, through a fixed point iteration. And if we translate this algorithm to our mean field game language, that is almost the same as our equilibrium correction algorithm, where there's a difference of a ratio. But this is definitely something that can potentially prove maybe the uniqueness and existence of the solution to the inverse problem. So now I want to conclude my talk. So the first thing I talk about is the learning in mean field game. Essentially, the thing I want to deliver is we can use the best response to analyze, to understand the mean field game system, and potentially we can also get some insight to develop algorithms for mean field game in high dimension and more complicated settings. And another thing is for this inverse mean field game problems, the value function phi0 seems to retain quite a lot of information of the ambient potential. And this is the case even when the viscosity is very large. So I will stop here and thank you for your attention. I will take questions.